Hi, everyone. Welcome to the AI session. Thank you all for coming. I'm Lior. I'll be chairing this session. And let's begin at the beginning. So without further ado, I'll present you the first speaker, Sofia Bobadilla, a PhD student at KTH. And Sofia will tell us about how to use AI to generate POCs from description.
Hi, everyone. Thank you so much for coming here on this morning. Thank you for the intro as well. To check that you're in the right room, the talk is from description to exploit AI engines for smarter audits. And I'm Sofia. I'm in the second year of my PhD, and I'm part of the research group that we call ourselves ASSERT, for Awesome Software Research Engineering Team. We are 4 around, so if you see more people like this, you know it's one of us. And yes, so you know I'm a PhD student and I have to give these talks a lot in academia, and always starts with like why smart contracts are so important, why the security is so critical. But there wouldn't be a DeFi Security Summit if it wasn't a huge problem, right? So I can skip that part. So let me just set the stage into our conception of the software development of a secure smart contract protocol, right? As in any software, you start by thinking about, okay, I want to do something, and I need to design and model how I want it to work. And then you give it into a development team to actually write the code, and ideally, they will test it. They will think about these security issues as well. And once they have a stable version, right, particularly in the blockchain space, we do security audits, which are extremely relevant because if you deploy the code, right, it's not being able to modify afterwards, and then a vulnerability can be extremely harmful. So in this process of a security audit, you rely on an external third-party service, which is extremely important because you want someone with a new perspective to look into your code and to find new scenarios in which you can be attacked. Yet, this process can be a bit of a bottleneck for your service to end up being monitored, which is the step in which you deploy the code and then you look into the transactions that are going and if something funky is happening, like an attack. The problem is that between step and 2, if something slips on, you get wrecked, and probably everyone gets wrecked because everything we're using on the blockchain has been audited by someone that probably is in this conference. So it's extremely important. So, as I mentioned, these audits are essential, like extremely important. I hope by what I'm saying here, you don't take it that I'm saying that we don't need it. We do need it, but they represent a little bit of a bottleneck because there is only so much budget you can put into your audit, and there is only so much time that you can put into it. So the idea is how we can make audits the most efficient way so nothing will slip through deployed code. And so there are some areas for improvement in here. We have seen a huge amount of AI agents coming, which the idea is to automate the detection of vulnerabilities. There are also overall improvements into vulnerability descriptions, right? So how a vulnerability works and relates, but still natural language code. And the last one, that is the one that involves in this talk, is proof of concept exploits. And here, for example, I put the guidelines from Immunify into how, if you want to submit a report with a proof concept, you should do it for Web3, which is still a bit different from Web2. And today I will show you I would like to call it our humble solution. So we thought, okay, we are using AI for generating software, right? And while vulnerability detection is still a problem itself, we thought we needed to separate them, because the way you will identify a vulnerability, it's a problem so complicated that if you include the generation of a proof of concept, that you're missing 2 very hard research areas. So we created POCO, which is an agentic way to generate proof of concept exploits for smart contracts. And here I put my collaborator. So Vivi Andersson is a PhD student on machine learning for security. Harald is a master's student in our group as well, and Martin is my supervisor. So what's the idea of POCO? So as I said, we don't do detection, and I want to make it very clear. We rely on a vulnerability annotation made by an auditor already. So they write this description. I believe I found a vulnerability here, and I believe this is the state it can be exploited, and this is how you can verify it. And then it gives us also the smart contract project in which the vulnerability exists. And then POCO, as I mentioned, is an agentic solution, so it has a React loop, which basically means POCO works autonomously with certain commands, and then it decides what to do afterwards. And we give guidelines of how it should do it and what should be the expected output. So for example, POCO here will immediately read the code base, try to understand what are the dependencies of the contract, and then once it finishes reading the code base, it will write a POC that then it has a tool to compile the POC and then to test. And then if the test passes, which we call it like all the assertions passes, it will output the POC exploit. But again, we are not also assuming that it will be correct by default. So of course, we always encourage auditors to don't trust, to verify. So our idea is that the output of POCO will be verified by an auditor that will later submit great reports, it will get great money, and then the developers of the receiver team will be super happy. So the whole idea of our work is that if we have better proof of concepts, we have happier auditors because they will know that they found the problem and they don't have to spend all this time that is taken to write the test because they know they already found a vulnerability. And with that, we also have better code fixes because a POC, it's an extremely powerful tool for the developer team to check that they are mitigating the exploit correctly. So a little bit on the architecture. So an agentic framework means that you give AI access to certain tools, and here you have to be super careful. If you read the details on the paper, we explain what are the security measures you need to take. So for example, POCO runs in a sandboxes environment where it won't have access to your secrets and so on. And it will give a set list of tools that it can utilize. And here we have like 3 categories. So like the basics tools, which are for code-based exploration, how to find the contracts, how to find functions and so on, how to write and how to read. And then planning tools, which is internal of the tool to decide what steps to do next and what steps needs to be done in order to achieve the goal, which is to create a proof of concept exploit that have test assertions that are derived from the natural language description. And then the tools that we include are smart contract tools, which are smart contract compile and smart contract test. And just to be very concrete, we are generating Foundry test for this. And you see here at the bottom, the task prompt is create a vulnerability exploiting proof of concept in Forge for the vulnerable contract at this path using the vulnerability description in 2. So we never let the AI decide what's the problem. We ask them to follow the annotations of the auditor. And again, we like being very concrete, so this is how POCO works. You say UV, run POCO, and then you call you give it the RP, which is the rec path. And that's the smart contract with the problem, and A is your annotation in a .txt file, and then you can choose the model. So we are mostly proposing the architecture to do it, more than bounding ourselves to one model. So the agentic architecture we created, you can use it with different models according to whatever you want to use. And yes, so I tried to add a GIF on the demo. I was a bit worried on the internet, so that's why it's a gift. So basically, you will give the parameters to POCO, and it will start by reading the contract. It will try to analyze. If you saw maybe too fast, it went to a globe to find more about it. And now let me check this other test, and it keeps operating. Now let me see how repayment works. And then it will eventually say, I already read what I need to, and now let me write the test. And it will execute it, and then the expected pattern is forge compile, forge test, and that it will only stop when forge test actually passes. Let me see if the GIF is working correctly. Yes, so then it writes, and then it will test it. NCP, Solidity Foundry, Forge Compile, and then test, and so on. So, okay, we say we love creating tools, but we love creating tools that we can actually verify, right? So we are researchers, and we will never blindly trust a process. I want to see, okay, you created this tool, but then tell me how did you validate it? So for POCs, we will say like 2 dimensions. You always start with the basic quality, right? So what will be the basic quality for a POC? It compiles, It contains assertions. It's AI hallucinates, so it's something that one should always verify. If you are waiting for a POC, it has to make sure that has any assert in between. And does the assertion pass? So that means we do forge compile, and then we do forge test. And then we do a grep on the code to check that there are assertions on it. And then the second, which is the most hard, which is how do I evaluate the correctness of a proof of concept exploit, right? And of course here, one can do manual validation, but then the results will be tied to the experience of the authors, which I would say is pretty fair, but we really love having these elegant oracles to validate it. So we said, okay, but what if we use the ground truth patch? So how does it work? Previously, we did an evaluation of code fixes for smart contracts. So we say, okay, if I want to generate automated code fix for a piece of code on smart contracts, I don't only want to know that it's still functional, I want to know that it mitigates the vulnerability that it originally had, right? But the problem was, when we did that first paper last year, is that we can only have so many exploits for a patch, right? So maybe my patch was mitigating a few exploits, but we still were a bit unsure of if it can stop all of them. But now if you go to the other way, right? I know there is a patch. I know that the patch has been accepted and the code has been deployed, so they really took care of the vulnerability. So if I have an exploit and I want to prove that the exploit is correct, if it's stopped by using the patch, then I know it's correct automatically. So that's how we did the evaluation. So first we evaluated if it was well-formed, right? Executable, contains assertion, and the assertions pass. And then for correctness, we execute the exploit, but on the patch code base. And then if the exploit fails, then we know that it's correct because the patch was accepted and it should stop all possible exploits. And it gives us a stronger assumption. So in order to evaluate, we created that dataset called proof of patch. When we go into vulnerability reports that have a hint of the solution by, for example, a link to a PR, a link to a commit, and then we manually look into it, and then we abstract the patch from it. So I'm gonna lie, 2 months ago, I was deep dive looking into Code4Arena, Sherlock reports, looking for this particularly. So vulnerability reports that have a description, ideally an impact, and that I can find that somewhere in there they wrote, this is the pull request that we utilize to address this vulnerability report. And some of them, of course, will contain a proof of concept that this is a prettier one that we did, but not everything in our dataset has it, but this is the outcome that we wanted to have. A proof of concept that sets the state of exploitation and then explains what's the steps to do, and ultimately has an assertion that tells me this is how I prove that the proof of concept actually, this is how I prove that the vulnerability actually exists. Yes, so here I put an example of a proof of concept generated by Poco. So it's quite verbose in the way that it summarizes the description of the auditor. And then we have contract, exploit test is fixture. In this particular case, it was a private pool that they wanted to demonstrate that you could get a flash loan with a very, very low fee that was incorrect according to the documentation. So you have the setup function that allows you to set the exploitation state. And then the most important test where the test flash loan incorrectly scale. And then it gives the steps of this is how the borrower only paid 25 way instead of 0.0025 ETH. And there it was another economic impact of the vulnerability. To be even stronger, you really need to take care of this. So we collect the results, right, across our data sets. And due to time, we managed to get 23 of them. And if you see that they have these IDs, it's because we did an overall scrapper of Solidit, and we enumerate the contracts, and then we manually went through all of them. So we only managed to look in the first best 100 that we did according to some prioritization. You can see the details on the paper. But from there, we only got 23. And if you see on the first part of the table, we have how many of them were well-formed, which meant, again, contains assertions, compiles, and the assertions pass. and then how many of them were correct, which means when we run them against the patch, vulnerable code with the patch base, the exploit will stop. And here, the champion sign means it's correct. IN meant that it was incorrect, and IC was, IN meant inconclusive, which means that the patch was actually a breaking patch. For example, the parameters changed, so then the exploit is not executable anymore. And IC meant that it was incorrect. So out of these 23 vulnerability reports, if we gather the results of POCO using those 3 models, which are GLM 4.6, which is an open source model, OpenAI 3, and CloudSonnet 4.5, for 22 of them, it managed to create a well-formed POC and a correct one for 20 of them overall. With this, we can say that POC generation automatically can produce correct and well-formed exploits for 80% of the reports that we did, that we provided another way to validate them, and that much research should be done in this area. With this, I thank you very much for your attention.
Thank you, Sofia. We have a few minutes for questions, so please.
Yeah, I would like to ask, how does POCO compare against using the Cursor IDE to generate the proof of concept with the same LLM?
You mean like you have Cursor open and then you describe the vulnerability?
I just take the same file, the same TXT file, and say to Cursor, this is the description of the vulnerability, write a test that exploits the vulnerability.
We didn't test it with the IDE.
Okay. Yeah, because I do that when I do audits, so I wanted to know if this is better than that.
Well, the thing I'm thinking right away is that it's not necessarily will understand how to test it right away. So like, for example, a common problem, it's the use of tools. And if you write the test in on a certain format, it will take some time for the agent to actually understand how to run it. So then you lose a lot of context in that process.
I mean, in my experience, it didn't happen, but it may, I don't know.
Okay.
But I use GPT-5 instead of those, so maybe that's I have a bigger context, I don't know.
I see.
Thank you.
Thank you for the question.
Any other questions? Okay, if not, let's thank Sofia again.